Hi there. Today in class we walked through an introduction to limits. We had an essential question for today's lesson. It was, how do we determine a limit graphically and numerically? And so I've picked two problems that are similar to the ones that you'll see on your homework assignment, one to demonstrate a numerical approach and one to demonstrate a graphical approach. Okay, so the one you see right here is number 1 in your textbook. It is a numerical approach. The purpose of a limit is to determine what y value does it look like our primary graph is going to touch as our x's get closer and closer and closer to 2. Right? And remember we talked about it doesn't actually matter what the y value is at 2. It may or may not be the same as the limit. It does not have to be the same as the limit. The limit is what it looks like it would be as we approach it. Right? And so in fact if we plugged in 2 to determine the actual y value, well, we'd get 2 minus 2 on top, which is 0, over 4, 2 squared, minus 2, which is also 0, 0 over 0, so we know that there's a hole there. Okay, but it doesn't matter, we're looking at the limit. And so the limit, we're going to go ahead and plug in these values, getting closer and closer to 2, 1.9, 1.99, 1.999, 2.001, 2.01, 2.1. We're going to plug those into this formula in order to isolate some y values that we then can use to project what our limit would be. And again, this is the numeric approach. Because we have our graphing calculators, we're going to go ahead and utilize our table function to help us fill in our table here. And so I'm going to go ahead and go to y equals on both the 84 and the 89 so that you can follow along with whichever type you have. And I've taken my formula here, my function, and I've plugged it into the y equals. Don't forget parentheses around the numerator and the denominator in order to make sure you're communicating to your calculator the entire denominator and the entire numerator. Okay, once you've done that, you're going to go to table, which on the 84 is right above the graph. So you're going to hit second to activate the blue, and then hit graph, so it goes to the table. And then on the 89, you're going to go alpha table, which is F5. And then you'll be able to input the different numbers. So we're going to input 1.9, and we get 0.34483. And so I'm going to come over here and write 0.34483. And from here on out, I'm only going to put them into one calculator because it's the same all the way down. So we're going to put 1.99, 1.999, 2.001, 2.01, 2.1. And so I have all of my y values here. 0.33445. Yeah. So now that we've selected our x values getting closer and closer and closer to 2, we can determine what our limit is by looking at the y values. What does it look like they're getting closer and closer to? Well, I notice here a pattern. I only have 1 3, and then I have 2 3s, and then I have 3 3s, and so I'm trying to figure out, okay, what would give me that pattern, 0.333 with increasing 3s? Well, my guess is 1/3, right? And so for the fun of it, I'm going to go ahead and plug in 2.00000. I'm just going to pick a lot of zeros, right? So it's even closer to 2 than 2 and 1,000th here. 1. And I'm going to get 0.3333333, which is, yeah, 1/3. And so my limit here, the y value that it looks like we are approaching, is 1/3. When it comes to a graphical approach, we have problems like this one. It's number 16 in your textbook. The limit as x approaches 0 of secant x, and they've given you a graph here. Okay, and so we're going to go ahead and approach 0. Well, when I follow my primary graph here, as I get closer and closer and closer to 0, it looks like my y value is getting closer and closer and closer to 1. Right? It looks like the y value should be 1. A similar type of problem would be if they asked you for the limit as x approaches pi over 2 of secant x, so using the same graph. But for this one, I'm going to go ahead and review one more time the 3 times where limits don't exist, in case you were absent. So when I'm looking here, as the limit as x approaches pi over 2 was I'm approaching pi over 2, and I know that the secant x graph continues, right, on the other side of the asymptote. And so we have, as we're approaching pi over 2, our graph is increasing without bound, right? It's going up to infinity. And this is called unbounded. It could go down to negative infinity as well, but anytime it's increasing or decreasing without bound, our answer is not a number, but a does not exist because the graph is unbounded. And there are 2 more cases where it does not exist. When it's unbounded, when it does not agree, right? So 2 graphs that approach like this. It doesn't agree here. It approaches this positive y value from the left and a negative y value from the right. This is does not agree, or oscillates. And all of this is in your notes as well. Right? And oscillates is when we have a function that as it approaches a certain number goes really, really fast back and forth between -1 and 1 before spreading back out again. And so right here, okay, it's oscillating, so it does not exist because it oscillates.